Hello, and welcome to the 10th lesson of the Big Data Hadoop and Spark Administrator course offered by Simplilearn. In this lesson, you will learn about data ingestion and the tools used for data ingestion. You will also learn about the working of Apache Flume and Sqoop. After completing this lesson, you should be able to explain data ingestion, list the tools used for data ingestion, explain the types of data ingestion, explain how Apache Flume works, explain how Sqoop works. In this topic, you will learn about data ingestion and tools used for data ingestion. Data ingestion is the process of importing, transferring, or loading data into a persistent storage layer. This enables data storage and facilitates usage of data either immediately or later. The process also involves modification or altering of data loaded from various sources. Ingesting data in HDFS, which is the storage layer of Hadoop, leverages its power to process, cure, mine, and analyze data. The following are tools available for data ingestion. Apache NiFi is an integrated data logistics platform with the following features. It automates the movement of data between disparate systems. It provides real-time control to easily manage data movement between any source and destination. It is data source agnostic and supports disparate and distributed sources that are differing formats, schemas, protocols, speeds, and sizes. These sources include different machines, geolocation devices, click streams, files, social feeds, log files and videos, and so on. It allows tracing of data in real time. Apache Flume is a distributed system for collecting log data from many sources, aggregating it, and writing it to HDFS. Its features are: it is reliable and highly available, while providing a simple, flexible, and intuitive programming model based on streaming data flows. It provides extensibility for online analytic applications. It maintains a central list of ongoing data flows, stored redundantly in Zookeeper. Apache Sqoop is a tool designed for efficiently transferring bulk data between Apache Hadoop and structured data stores, such as relational databases. Features of Sqoop are: it offers two-way replication with both snapshots. It supports the incremental load of a single table or free-form SQL queries. It allows saving jobs of repeated runs so that the latest updates can be imported. It allows importing data into Hive or HBase tables, as well as exporting data from HDFS and RDBMS. Apache Kafka is a distributed publish-subscribe messaging system with the following features. It is designed to provide high-throughput, persistent messaging that is scalable and allows for parallel data loads into Hadoop. It uses compression to optimize I/O performance. It uses mirroring to improve availability and scalability, as well as to optimize performance in multiple cluster scenarios. Amazon Kinesis is a fully managed, cloud-based service for real-time data processing over large distributed data streams. It can capture and store terabytes of data per hour from numerous data sources. Chukwa is a Hadoop subproject that bridges the gap between log handling and MapReduce. It provides a scalable, distributed system for monitoring and analysis of log-based data. Apache Storm is a general-purpose event processing system, which is ideal for batch mode processing over massive datasets. It is a distributed, real-time computation system for use cases such as real-time analytics, online machine learning, and continuous computation. Goblin is an Uber ingestion framework which takes internal and external datasets through a single framework. It is a universal data ingestion framework for extracting, transforming, and loading large volumes of data from a variety of data sources into Hadoop. Data sources include datasets, REST APIs, FTP, SFTP servers, filers, and so on. Goblin handles the routine tasks required for all data ingestion ETLs, including job or task scheduling, task partitioning, error handling, state management, data quality checking, and data publishing. It also manages metadata of different sources in one place. Fluent is an open-source data collector for unified logging layer. It decouples data sources from back-end systems by providing a unified logging layer in between. Cloudera Morphlines is an open-source framework that reduces the time consumed in building and changing Hadoop ETL stream processing applications that extract, transform, and load data into EDW, HDFS, HBase, or Apache Solr. Apache SAMSA is a distributed stream processing framework. It uses Apache Kafka for messaging and Yarn for fault tolerance, processor isolation, security, and resource management. Data ingestion can be categorized into three main types: batch data ingestion, streaming data ingestion, structured data ingestion. Batch data ingestion. In this type of ingestion, the file system shell includes shell-like commands such as copy from local, put, copy to local, or get, which can be used to write data from a local file system to HDFS or other file systems that Hadoop supports. Streaming data ingestion. In this type of ingestion, advanced packages such as Apache Flume, Chakwa, Kafka, or Storm can be used to stream data into Hadoop for real-time analytics. Let us discuss how Flume is used for streaming data ingestion. Flume employs a producer-consumer model. Entities through which data enters into Flume are called sources. Sources either pull actively for data or passively wait for data to be delivered to them. The entity that delivers data to destination is called sink. Flume has many built-in sources, such as log4j and syslogs, and built-in sinks, such as HDFS and HBase. The conduit between the source and the sink is called channel. Sources ingest events into the channel, and then sink drains the channel. Channels allow decoupling of ingestion rate and the drain rate. When the rate of data generation is more and cannot be handled by the destination, the channel size increases. Later on, you will learn about data ingestion with Flume in detail. Apache Chakwa is used for large-scale log collection and analysis, and is set up on top of the MapReduce framework. Apart from data ingestion, Chakwa also includes a flexible and powerful toolkit to display monitoring and analyzing results. Chakwa is a mini batch system and not a continuous stream processing system like Flume. Apache Kafka and Apache Storm may also be used to ingest streaming data into Hadoop. Structured data ingestion. In this type of data ingestion, applications such as Apache Sqoop can be used to import data from a relational database table into HDFS. The import process is performed in parallel and thus generates multiple files in delimited text, Avro, sequence file, and other file formats. Sqoop can also be used to export data such as the results of MapReduce processing back to the relational database for consumption by external applications or users. In the previous screen, you learned about the types of data ingestion and briefly discussed how streaming data ingestion is handled by Apache Flume. In this topic, this will be discussed in detail. The following features of Flume enable ingestion of high-volume streaming data into HDFS. Ingestion of stream data. Flume can ingest streaming data from multiple sources into Hadoop for storage and analysis. Insulate systems. Flume has a buffer storage platform for impermanent spikes when the rate of incoming data exceeds the rate at which data can be written to the destination. Guaranteed data delivery. Flume uses channel-based transactions to ensure reliable message delivery. When a message moves from one agent to another, two transactions are started, one on the agent that delivers the event and the other on the agent that receives the event. This ensures guaranteed delivery. Scale horizontally. Flume can scale horizontally to ingest new data streams and additional volume as needed. Typical source streams are application logs, sensor and machine data, geolocation data, and social media. Hadoop and HDFS work best on large files of at least 64 MB or 128 MB. However, a number of small files are generated in the data center due to scale-out architectures. Tools, such as Flume, help to overcome this mismatch of file sizes. Observe the diagram to understand how Apache Flume works to handle streaming data ingestion. Data can be stored in any of the centralized stores, such as HDFS or HBase. When the rate of incoming data is more than the rate at which data can be written to destination, Flume acts as a mediator and ensures a steady flow of data. Flume is reliable, fault-tolerant, scalable, manageable, and customizable. Apart from log files, it can be used to import huge volumes of event data produced by social networking sites such as Facebook and Twitter, and e-commerce websites such as Amazon. In order to understand how Flume handles data flow, it is important to understand the following terminologies. Flume Agent. Flume Agent is a Java virtual machine, or JVM process, that hosts the components through which events flow. An agent runs one or more channel and sync sets through a flow multiplexer. The multiplexer either replicates or selectively routes an event. A Flume agent contains at least one source, one channel, and one sync. Flume Event. A Flume event is a unit of data flow that contains a payload, which is the actual information or message in the transmitted data, and an optional set of string attributes. An event is transmitted from its point of origin, usually a client, to the source of an agent. When the source receives the event, it sends it to a channel that is a temporary store for events within the agent. The associated sync can then remove the event from the channel and deliver it to the next agent, or the event's final destination. The image on the screen illustrates the Flume architecture and shows how channels connect sources and syncs. Flume is a framework used to move log data or similar data into HDFS. Log servers generate events and log data. These servers have Flume agents running on them. The image on screen illustrates how data flow is handled by Flume. Flume handles data flow in the following manner. Agents receive data from data generators. Intermediate nodes called collectors collect the data in these agents. Data from collectors is aggregated and pushed into centralized storage such as HDFS or HBase. Data flow in Flume takes place in the following three ways. Multi-hop flow. When an event travels through more than one agent before reaching the final destination, it is called multi-hop flow. Fan-out flow. When data flows from one source to multiple channels, it is called fan-out flow. Fan-out flow is of two types. Replicating. In this type of data flow, data is replicated in all the configured channels. Multiplexing. In this type of data flow, data is sent to a selected channel whose identity is mentioned in the header of the event. Fan-in flow. When data is transferred from many sources to one channel, it is called fan-in flow. Adding Flume service to CDH cluster. In this demo, you will learn how to add Flume as a service to the Hadoop cluster. Flume as a service can be used to add streaming or unstructured data into HDFS. To add Flume, click on Actions, then on Add as Service. From the list of services, select Flume and click Continue. You will be asked to select the set of dependencies for your new Flume. Select the option that has HBase, HDFS, and Zookeeper, and click Continue. Next, you will be asked to select a role for Flume-related role. Click on Select Hosts. select the IP address that has 161. Click OK. Click Continue. You will then get a message, "Congratulations, your new service is installed and configured on your cluster." Click Finish. This will show you the list of all services. In the list, you will see that Flume is added as a service, but it is in stop status. To start your Flume, click the arrow on the right side, and from the list, click Start. This will start the configuration for Flume. Once the configuration is done, you can see that the Flume is in good health status. This brings us to the end of the demo on adding Flume as a service to your Hadoop cluster. In this topic, you will learn about how structured data ingestion is achieved with Sqoop. The following are the features of Sqoop that support structured data ingestion. It can import sequential data sets from the mainframe. This supports the growing need to move data from the mainframe to HDFS. It can import directly to ORC files. This improves compression and facilitates lightweight indexing for improved query performance. It can move certain data from external stores and EDWs into Hadoop to optimize the costs of combined data storage and processing. It can support parallel data transfer to achieve faster performance and optimal system utilization. It can speedily make data copies from external systems into Hadoop. It improves efficiency of data analysis by combining structured data with unstructured data in a schema-on-read data lake. It achieves load balancing and mitigates excessive storage and processing of loads to other systems. The image on screen illustrates the working of Apache Sqoop. Sqoop connects to external systems in an optimal way through a pluggable mechanism. With the Sqoop Extension API, new connectors are embedded into Sqoop installations to connect to various systems. Sqoop comes bundled with various connectors that support connectivity to popular database and data warehousing systems. Sqoop automates the process, and the database describes the schema for the data to be imported. Sqoop uses MapReduce to import and export the data in HDFS or directly in Hive in HBase. This allows parallel operation and achieves fault tolerance. Sqoop integrates with Apache Oozie, which coordinates the workflow and allows scheduling and automation of import and export tasks. Sqoop 1 has some challenges in terms of usability, extensibility, and security. Cryptic and contextual command line arguments lead to errors in connector matching. Tight coupling between data transfer and the serialization format causes issues. Some connectors support a certain data format that others don't. For example, MySQL connector can't support sequence files. There are security concerns with openly shared credentials. Root privileges are required for local configuration and installation, and thus these tasks are difficult to manage. Debugging the map job is limited to turning on the verbose flag. Connectors have to follow the JDBC model and use JDBC vocabulary, such as URL, database, table, and so on, whether it is applicable or not. Sqoop 2 overcomes the challenges of Sqoop 1. Following are the features of Sqoop 2 to overcome the challenges of Sqoop 1. Sqoop 2 provides a new web-based user interface, using which a user can walk through an import or export setup easily. Various built-in connectors ensure a user is not tasked with installing or configuring connectors. These connectors communicate the necessary options to the Sqoop framework, which then translates them to the UI. The UI is built on top of a REST API that can be used by a command client, exposing similar functionality. The image on the screen shows the Sqoop-2 architecture. In terms of usability, Sqoop-2 is installed and configured on the server side, and thus providing all connectors and drivers in one place. Database connectivity is needed only on the server. It provides a web-based service, a command line interface, or browser as the front end, and a metadata repository in the back end. Sqoop-2 integrates with Hive and HBase on the server side. It decouples itself with Oozie, and Oozie manages Sqoop tasks via REST API. A new Sqoop container need not be installed in Oozie. With respect to ease of extensibility, Sqoop-2 does not restrict usage of only JDBC connectors. In addition, connectors are now responsible only for data transport. Web-based UI eliminates the chances of user errors and enables users to choose the connectors. In terms of security, Sqoop-2 operates as a server-based application and supports secure access to external systems by providing role-based access to connection objects. Thus, users can use Sqoop-2 with a minimal understanding of its details by using a web-based application to run Sqoop. This allows Sqoop to be installed once and used from anywhere. Sqoop also integrates better with external systems such as Oozie, since it uses REST API for operation and management. Adding Sqoop service to a CDH cluster. In this demo, you will learn how to use Sqoop to add data into a Hadoop cluster. Sqoop is a service or a tool which can be used to add structured data from an external RDBMS to your Hadoop cluster. To add data into HDFS, you require Sqoop. First, add Sqoop as a service. Click Actions, then Add Service. You will have a list of services like Flume, which can be used to aggregate data from almost any source into a persistent storage such as HDFS. This can be used for unstructured data. By scrolling down, you will see an option Sqoop-2, which is a tool designed for efficiently transferring bulk data between Apache Hadoop and structured data source like relational databases. Select Sqoop-2 and click Continue. You can customize the role assignment for this new service. By default, it shows the Sqoop server at 160 as the IP address. Click on the IP address to edit. Select IP address, which has 161, and click OK. Click Continue. You will see the configuration of Sqoop, like the database that will be used by Sqoop, and other details. Click Continue. Once you click Continue, the process of adding Sqoop to your cluster will start. Once Sqoop is added, the Continue button is enabled. Click Continue. You will see a message which says, "Congratulations, your new service is installed and configured on your cluster." Click Finish. Go back to Clusters, and in Services list, you can find that Sqoop-2 has been added as a service. Click on Sqoop-2. You will see the instances that the Sqoop-2 server is running. Click Configurations to check Sqoop-specific configuration properties. This is the process involved in adding Sqoop as a service to transfer data from external RDBMS to the Hadoop cluster. Using Sqoop to import data into HDFS. In this demo, you will learn how to use Sqoop to ingest data into HDFS. As you can see, Sqoop service is already added into the cluster. Sqoop can be used to ingest data from an external RDBMS. For this, you need to first install a new RDBMS, or you can use an existing RDBMS. Now, use PuTTY configuration application to connect to the machines. Let us connect to the first machine of the cluster by selecting M1 in the Saved Session tab. Now, click Load and click Open. From the Management Console, you can see that there are 3 machines, M1, M2, and M3. Once you have connected to the machine, to install the SQL, you can log in as root in the terminal by typing in sudo su. You can see the MySQL RPM. Based on the Linux version, you can download the RPM from the internet by going to the SQL page and typing Install MySQL on Red Hat Linux in the address bar. Now, search for the MySQL link. After going to the MySQL link page, scroll down to find the link http://dev.mysql.com/downloads/repo/yum and click the link. With this link, you can go to the repository to download the MySQL version for your Red Hat Linux or for any distribution. Now in the Download MySQL Yum repository page, scroll down and click the link Download for Red Hat Enterprise Linux 7. This will take you to the download page. Right-click No thanks, just start my download, and select Copy Link Address. Once you have copied the link address, go to the terminal and type wget. Right-click to paste the link address that you have copied and hit Enter. Now type RPM-IVH MySQL 157-release-e17-9.noarch.rpm and hit Enter. Now type yum install MySQL-server and you will be able to install SQL on your machine. Once MySQL is installed, type MySQL to log into MySQL. It will give you Access Denied error message because it expects you to give a password, and since you have not set up a password, you cannot change the password for the root. Now, to set up a password for MySQL, use the following commands. First, you need to stop the MySQL service. Then, you have to select the Set the MySQL Environment option. You will have to start MySQL service again. Now you can log in as root. You will not be asked for a password. Once you are in MySQL, you have to update MySQL.user service and set a new password. You can also select Flush Privileges and then quit. Now you need to stop MySQL and then select the Unset the MySQL Environment option. Then select the Start MySQL Normally option. You will be able to log into MySQL with a new password. Once this is done, you can grant some privileges. To grant privileges, you might have to alter user to give a particular password. Also, you can grant privileges to different users to log in from different machines to MySQL. Once MySQL is installed, go to the terminal and try it out. Now type the MySQL-u root-p command and type in the password, and you will be able to log in to MySQL. Now type Show Databases and you will be able to see the databases. Now type Use MySQL, and then type Show Tables. You will be able to see all of the tables within the databases. Now you can import one or all tables into HDFS using Sqoop. As you can see, the last table is shown as user, so you can query the table by typing in Select User Host from User. Now you will be able to see all the users and machines from which the users have access. Now type Exit to come out of the MySQL path. Now MySQL is ready to import data, but you also need a MySQL connector jar file, which you already have. Now, to get the information about the MySQL connector jar file, go to Google and type JDBC MySQL connector. Now you can go to the link where you can download the JDBC connectors. In the Download Connector/J page, click Download adjacent to Platform Independent, Architecture Independent, Compressed tar archive. After this, right-click on No Thanks, Just Start My Download, and select Copy Link Address. Now, go back to the terminal and type wget. When you use the right-click button, you will be able to get your connector tar file. Once you get your connector tar file, untar it by typing in tar-xvf, mysql-connector-java-5.1.40.tar.gz. So now a directory containing MySQL connector is created. You need the directory because you cannot get information about your MySQL connector jar file, which contains the driver that allows you to connect Sqoop to HDFS. In order to connect Sqoop to HDFS, you need to copy the jar file into the /var/lib/sqoop2 directory. Type the command cp mysql-connector-java-5.1.40-mysql-var/lib/sqoop2. Now you can check the MySQL jar file by typing in ls/var/lib/sqoop2. Now you can use Sqoop to import data to HDFS. Log into HDFS by typing in su-hdfs. Then type hdfs dfs-ls/ to check the data you have in the cluster. Now you are able to see the different directories you have. Now you need to type Sqoop help to show the options of Sqoop. You will be able to see the different options available in Sqoop. The options will enable you to create Hive tables, import data, import all tables, import from mainframe, list databases, and list tables. You can test the connection by using Sqoop. To do this, type in Sqoop list-databases -connect jdbc://mysql:// 10.0.0.161 --username root -P and hit enter. Now type the password to access MySQL. you will be able to see the list of databases that are available in MySQL. As the connection is working fine, to import a particular table, type sqoop list-tables --connect jdbc://10.0.0.161/mysql username root --P and hit enter. Now you can import all the tables or import one by one. Sqoop will trigger a MapReduce job to import one or multiple tables. Now type sqoop import -connect jdbc://mysql:// 10.0.0.161/mysql --username root --P -table help _keyword -target -dir /myimptbl and hit enter. Now type in the password and you will be able to see that the import has started. Meanwhile, you can look at the job by going into Resource Manager UI for the job that is running with the job ID. As you can see, the job is using some variables which are shown on the screen. As you can see, you are receiving the message, User Access Denied, for the user that is trying to connect to the HDFS. You need to cancel the job process. Now you need to try running with a different user. So type sqoop import -connect jdbc://mysql:// 10.0.0.161/mysql -username HDFS -P -table help _keyword -target -dir /myimptbl and hit enter. Now type the password and start the import again. If you have user access problems, you need to change the user. As you can see, there is another error message. User directory already exists, and the job process has been stopped. You need to change the output directory, so type sqoop import -connect jdbc://mysql:// 10.0.0.161/mysql -username HDFS -P -table help _keyword -target -dir /myimptbl1 and hit enter. Now type the password and start the import process. As you can see on the screen, you are able to import 681 records. To verify this, type HDFS DFS -ls/ and hit enter. Now you will be able to see the directory myimptbl1, which you had created recently. Now you can look into the directory myimptbl1, type in HDFS DFS -ls/ myimptbl1, and you will be able to see the files related to the directory. To look into a particular file, type HDFS DFS -cat/ myimptbl1 / part -m -00001 and hit enter. Similarly, you can run the sqoop commands to import the data. Let us now look at how to change the output directory and how to compress the data. To do this, type sqoop import-connect jdbc://mysql:// 10.0.0.161/mysql-username hdfs-P-table help_keyword-z-target-dir/myimptbl2 and hit enter. Now type the password and hit enter. After running the job process, you can check if the job process was successful by typing hdfs dfs-ls/. Now, as you can see, the directory myimptbl2 has been created. Now, let us look in the directory to see the related file. Type hdfs dfs-ls/myimptbl2 and hit enter. You can also see that the data is in compressed format with .gz extension. Now, if you compare the myimptbl2 table with the myimptbl1 table, the data in the myimptbl2 table has been compressed. You can also import the data in different formats. To do this, type sqoop import-connect jdbc://mysql:// 10.0.0.161/mysql-username hdfs-P-table help_keyword-as-sequence file -target-dir/myimptbl2 and hit enter. Now type the password. Now you will be able to see the imported data in sequence file format. As you can see, the job has been successfully run. Now you can check if the data has been imported into the directory by typing hdfs dfs-ls/myimptbl3 and hitting enter. You will now be able to see the different files inside the directory. To look at a particular file, type hdfs dfs-cat/myimptbl3/part-m-00001 and you will be able to see the data in binary format as you have imported the data in sequence file format. So, you have successfully imported data to the HDFS using Sqoop. Now click Cluster and click Hue Service from the Status tab. As you have added Sqoop as a service, click Hue Web UI. Now click Data Browsers and select the Sqoop Transfer option. After this, you will be directed to Hadoop Sqoop, and you will be able to see Manage Links and New Job Links. Now click New Job and fill in the details by providing information in the Name and From link fields. Now click Add a new link and provide details in the fields. Now click Save. You have created a connection as shown. You can also create another connection and click Next. Once the connection is established, fill in the details in the database page as shown. Now click Save, and you will be able to run the job. So, you have seen how you can use Hue or Sqoop terminal to submit a Sqoop job.